Hi, everybody. A little off schedule here, but it's Christmas time and it's holidays, and so do it when you can. All right. So anyway, let's see, where are we at? Oh, let's fix the camera there. All right. So where we left off was we were just going to start functions, and I'm looking at this going methods, closures, higher order functions, and diverging functions. Okay, this is some diverging functions. Terminology I haven't heard before. All right, so let's see what's going on here. Functions are declared with the function keyword. Or a fun keyword. We've used that before. Its arguments are type annotated like variables. We've done that before. And if the function returns a value, it must be specified with the arrow. We've done that before. The final expression of function will be used as a return value. Right, we've done that before. Alternatively, the return statement can be used. We've done that before. And you can use return from inside of statements and loops. Okay, yes, we've done that before too, I think. But if we haven't, it's pretty obvious how we could do that. Okay, so we got fizzbuzz. Function main, fizzbuzz2 is divisible by fizzbuzz, blah, 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 fizzbuzz, buzz, buzz, buzz. Okay, cool. So we have, all right, so, we've got different functions, and this one returns the unit type if it doesn't actually return a value. This one, now this is interesting. Oh yeah, no, that's not. Sorry, I thought this was a loop, but it's not. N u32 for n dot dot equals n fizzbuzz n. Right, so we're doing a function. This one doesn't return anything. We can just skip that part, but we can always be explicit and say it returns, I guess. And this one returns a Boolean to say is divisible by left-hand side, right-hand side equals 0, and that returns true or false because that's a comparison equals. Okay, yeah, nothing too surprising here. Let's move on. Okay. Associated functions and methods. Some functions are connected to a particular type. Associated functions and methods. Associated functions are functions that are defined on a type generally, while methods are associated functions that are returned a particular instance of a type. So we have a struct, impl point. We've done this before. But we did impl point because we wanted to do like a print, and this there's no like, oh yeah, we're doing a print. It's just a regular, we're implementing implementation on point. Okay, so this is how we're going to attach methods to objects or structures in this terminology. This is an associated function because it's function. We've done this before. All of this, and here's structure rectangle. This is a method in rectangle. Self is sugar for self, where self is the type of the color object. In this case, self equals rectangle. Okay. That's a lot of words. So how is this? So this is point. So we have origin, we've got new, and this is area and perimeter and translate, but I'm not sure that. Oh, hang on. Maybe because this is. Oh, I see. So this is a simple one, right? Point. We can create a point at the origin, and this one is we can create a new point with those parameters. This one, we're using self as a parameter, which is the rectangle structure that we're related to. So we can have, I guess, if I was going to relate this back to C Sharp or maybe even Java, this would be a static function because it doesn't take the object. It doesn't use anything about x and y of this particular point. So these would be static functions. They do the same thing regardless of what point is. And these would be instance functions because they would be related to this particular rectangle. Okay. And you're going to call these associated functions, and methods. Okay, all right. I'm trying to remember that terminology. So methods are attached to, or are attached to the instance. Associated functions are attached to the class itself. So yeah, so it's like static functions and okay, all right. But there's nothing really any different. Like you don't have to use a special keyword or anything. You just don't pass the self into here. And it's interesting that it's ampersand self. Ampersand self is sugar for self colon ampersand self, where self is the type of the caller object. Okay, so that is the type of the caller object. So we could have written that instead, I guess. All right. Oh, and this method requires the caller object to be mutable. So mut self, desugars self colon mut self. Okay, whatever. And then a pair owns resources to heap allocated integers. Oh, box. Remember I had that problem with box before? Now this is kind of giving me a clue. Box says these two things are allocated on the heap. So there's the stack and there's the heap, right? There's the two places where you can allocate memory. I think we read before in here somewhere that most of this stuff is allocated on the stack. But this is saying if we use box, it's going to allocate it on the heap. Thanks for the clue. Okay, I think I understand box a little better. And because I was trying to unbox something and it wasn't really going that well. But I kind of get it now. Okay. All right, so these are on the heap. So how do we reference things that are on the heap? This consumes the resources of the caller object self, desugars self. Oh, and this is, okay, so pair, self, first, second, destroying pair. This method consumes the resource of the caller object self. Oh, sorry, this method consumes the resources of the caller object, period. Self desugars to self. This method consumes the resources of the caller object. Destroy self. Oh, okay, and it's a destroy. And we are create a new pair, print it, and then it's gone. Oh, because we've copied it. What? Oh boy, this. Okay, so it's on the heap. We grab the pointer and use it here, and because we've taken ownership of it, then that no longer has ownership. Yeah. All right. All right. I'm struggling with that one. All right. Let's see. Rectangle. Okay. Yeah, we don't care about that. Rectangle point. What is this? This one is pair. What I care about is the pair stuff. Error. Rectangle is immutable, but this method requires a mutable object. Rectangle translate. Okay, mutable objects can be called mutable methods. Translate. Ooh, okay. Pair, new 1, new 2. New? What's new? There's no new here. Oh, is this must be. All right. This is worth copying because there's I have questions. All right, copy. Let's pop over to here. All right, you know what? We can close this from last time. Close folder. All right, and we're going to create a new terminal. change directory to, where are we going? We are going to c:/rust. Okay, and cargo new. What should we call that? Oh, methods, I guess. Okay. We don't need to change directory. Methods, file, open folder, Rust, methods, select folder. Okay, source, main, select all, paste, and let's just run this once just to see what happens. Okay, rectangle perimeter 14, rectangle area 12, destroying pair 1, 2. Okay. All right, fine. So new, but this, it's interesting because point. Oh, hang on. Point has a new. So we've defined something called new for point. So when we go here in main and say, okay, create a new point and then use origin, right? We've got the method for origin, we've got the method for new. Methods are called using the dot operator, rectangle dot perimeter, and that takes self and returns an F64. Oh, the rectangle dot perimeter is the same as rectangle, capital R rectangle, the where is it? There, rectangle, this structure, rectangle, colon perimeter. Oh, so I can call it both ways. All right. So I can choose to that, so that instance method can be called either with the instance or, oh, okay, that's interesting. So let me just, let's see, rectangle, emitter, get out of the way, rectangle, colon, oh my goodness, ampersand rectangle. You claim that that's the same thing. Let's run that. Oh shoot. There. Let's run that again this time with the proper syntax. Rectangle perimeter 14. Okay, so yes. So that is the same. That's interesting that that's the same. All right. So we can either reference it by the object, the definition of the object, or we can reference it as the instance. It kind of makes it's easier to do the instance if you actually care about the perimeter of that specific rectangle. You don't have to pass it. But I suppose there will be times when I may want to pass multiple things, and that would be easier. Okay. All right. Square is a rectangle. 1, sure, whatever. Error. Rectangle is immutable, but this method requires a mutable object. So rectangle.translate. Oh, mut. We've got mut square. Okay, so that's mutable. But so if we do this, translate. That's going to give me an error because cannot borrow a rectangle as mutable as it is not declared as mutable. Okay, so fine, fair enough. So we can't translate this rectangle, but we can translate the square, which we've defined as immutable. Now that actually says that this maybe is limited in its abilities because, well, I guess not really. Because if I pass, where's perimeter, perimeter, no, translate, what was I looking for? It was, so translate. So if I did capital R rectangle, colon, colon, translate, and then I can pass brackets rectangle 1.0, 0.0. Alright, and now let's save that. And now this is telling me that, yeah, I expected a mutable rectangle. Okay. So I guess if I have let mut r equals can I do p1 colon rectangle dot p1 p2 rectangle dot p2. All right, and then I can do r here. Are you happy? Oh, no. Why aren't you happy? It says, consider mutably borrowing here. All right, so if I copy the, because this is originally not mutable, so it doesn't actually matter that I said this. I think we ran into this last time where I had to make a copy of P1 and P2 and then I could allocate them. So this doesn't automatically make a copy because it's still complaining about R. Let me just change that to rect because then I'll be able to rect. Okay, so this is still underlined. Is mismatch types expected mut rectangle found struct rectangle, but it's I don't. No, that's not going to do it. So if I change this to 7 and 7, so just initialize it to some other numbers. Is it now happy? What's the oh, found integer. Okay. Oh, it needs to be a point. Because these points are not mutable. Where did square? Let me see. Where did we? So, all right. I need to create a new point. Point. Right. 1.0. 1.0. Point. 2.0. 2.0. Now, what's the problem? Sorry. Colon, new. There. that was my C# syntax peeking through. Okay, so if I create new points, then it's oh, is it still not happy? What is going on here? Why is it not? Oh. I don't understand. Why are you not happy? I don't get it. Why are you not happy? Translate. Oh, or do I need to say, this? Oh, I need to say that. But it's mutable already. Why do I have to tell you again that it's mutable? Because it was already mutable. So let me go backwards. Because it was telling me that from the beginning, and I wasn't listening. All right, let's try that. And now, if I say ampersand mut rect and save that. Oh, and now it's happy. Oh, sorry, semicolon. Maybe now it's not happy anymore. Yeah, now it's happy. Okay, so all along, I needed to do that, and it would be happy. So this is, so my question is, because I translated this, am I modifying the original rectangle, or am I not? All right, so let's set a breakpoint here. Let's save this. Let's debug this. Run and debug. Okay. Okay. Yes. We're happy with the configuration. Thanks very much. All right. So we got to here. Now, originally, rectangle. What is rectangle? Oh yeah. So P0 is origin, so 0, 0, and P1 is 3, 4. So when we go to rectangle, it's still 0, 0, 3, 4. Okay, so we did not modify the original, but rect is 1, 2, and 4, 6. So we moved, 1 and 1 and 2 and 2. Okay, so sure. So what that means is that this made a copy into a different memory location, and that we modified that other memory location by saying, okay, here we have this mutable rect, which takes a copy of those things, and then we translated that. Okay. All right, so I think we've run into this. We did this last time too, but I'm still trying to drill this one into my head. So we're not modifying the original. We are modifying the copy in this particular case with the translate. And yeah, now that I say that out loud, I do remember we kind of learned this last time, but we did not. Okay, so let's step. Okay, pair box new 1 new 2. Okay, so this is pair, and what are you trying to tell me here? Okay, and I'm not sure what this is trying to say to me. Oh, I think it's probably looks like it's an address. That looks addressy. So then if we destroy it, let's F10, step one more. Okay, and pair is gone. Okay, and I guess it was trying to get us to delete this. And let's see if we can, we'll just save that and we'll rerun this. We'll run the debug one more time. Oh, we have to finish. Continue. Now, debug. Ooh, and what's going to say? Oh, no, this value used here after move. Pair move due to this method call. Oh, so it's not even going to let us run. Move occurs because pair has type pair, which does not implement the copy trait. Okay. Pair moved due to this method call. Okay, it's moved, and now the value after the move doesn't exist. Okay, so we're not even going to be able to run this, I don't think, now, because the compiler is not going to let us do this. Okay, fair enough. Good on you, compiler, for figuring that out. That's good. So we don't have to, at runtime, discovering this at runtime would not be as much fun as discovering this at this point, which I'm all in favor of. Okay, so this new here allocates memory on the heap and then places X into it. Doesn't actually allocate if T is 0 sized. Okay, so we've created, whoops, I'm going to follow their example here. Well, no, not going to be able to scroll within that. I think, is that it? Oh, I think that may be it, the whole example. That 5 box new 5. Okay, so we still don't know how to unbox anything, but this pair expects pair expected a box, right? Where's pair? Where are you, pair? There, box I32, box I32, yeah. So it expected a pair, and it got a pair, or a box, so fine. And then, because it's on the heap, I guess we can destroy it by looking at it. This is like a physics experiment. And so we have the Schrodinger's cat, and by looking at it, we have removed one of the options. All right. So okay, cool. Still not quite sure what I'm going to do with that information. All right, let's move on here. Is there what else was there? Yeah, here we go. I'm getting more sparkles today. Look at that. The light keeps changing on me. It's kind of sad, actually. Why did you change? Anyway, okay, so we did all of that. There's nothing here, nothing to try other than the stuff we've already tried. All right, so a little more information. Closures. Closures are functions that can capture the enclosing environment. For example, a closure that captures the X variable. Okay. The syntax and capabilities of closures make them very convenient for on-the-fly usage. Calling a closure is exactly like calling a function. However, both input and return values can be inferred, and the input variable names must be specified. Other crafts are using vertical bars instead of brackets around input variables. Optional body delimitation for a single expression. The ability to capture the outer environment variables. Okay. Not really understanding yet. Okay, increment via closure and functions. So here's a function. We're adding 1. We're returning an I32. We're taking the I32 that came in and we're adding 1 to it. Closure's anonymous. Oh, anonymous functions. Here we are binding them to references. Annotation is identical to the function annotation, but is optional. These nameless functions are assigned to appropriately named variables. Well, then we've named them, have we not? Whatever. Closure annotated. So we're taking I32 as a parameter, and we're returning I plus 1. And we can also just say that. And us programmers, if there's less typing we can do, we're going to do it. So obviously the inferred option is the one that everybody probably writes. All right. Call the function enclosures. Function, closure, closure. I don't get it. Why? What? What? Why do we care? Why? But it's you're calling it exactly the same way as you call a function. So how is this helpful? I don't, or maybe there's some other thing. Once closures type has been inferred, it cannot be inferred again with another type. Cannot use closure inferred with another type. Closure inferred. Okay. To do, uncomment the line above and see the compiler error. Okay, so we started off with I, which was an I32. And we pass in an I64, and it's going to give us an error. A closure taking no arguments, which returns an I32. Okay, going to return 1. All right, so there's something here about the ability to capture the outer environment variables. And I think that's maybe the key to all of this, although they're not demonstrating it here. But I assume what that means is that, well, I don't know. So let's move on to capturing, because I think it's going to tell us right there what this is all about. Okay, closures are inherently flexible and will do whatever the functionality requires. This allows capturing to flexibly adapt to use cases, sometimes moving, sometimes borrowing. Closures can have capture variables by reference, by mutable reference, by value. Okay, preferentially capture variables by reference and only go lower when required. Okay. Oh, so here is a two vertical bars. So we're passing no parameters, and we're calling this. And we have color. And color comes from here. So here's an example of the capturing variables, right? Because the closure to print color, which immediately borrows color and stores the borrow and closure in the print variable, it will remain borrowed until print is used at the last time. Print line only requires arguments by immutable reference, so it doesn't impose anything more restrictive. Okay. Call the closure using the borrow. Print. Okay. Color can be borrowed immutably again because the closure only holds an immutable reference to color. Reborrow, %color, print. A move or reborrow is allowed after the final use of print, so we're moving it there. Okay. Let mutable count equals 0. A closure to increment count could either take either one of those, the mutable or the thing, but mutable count is less restrictive, so it takes that, immediately borrows count. Mutable is required on inc because mutable is stored inside, thus calling the closure mutates the closure. Oh dear. Okay. So inc needs to be mutable because this is mutable and we are mutating it. This takes no parameters. This is the function that we're calling. All right. And then we can increment. So I suppose, yeah, okay, I can see that. We if we want to do the same little bit of action over and over and over again, we can define it in this context, not actually create a function for it. Because the function, it may get messy, and we're going to have like functions scattered throughout. We're going to have lots of little functions, but if we can do this one thing, the count plus equals 1, then that's fine. And then, okay, the closure still mutably borrows count. An attempt to reborrow will lead to an error. So if we try to do that, that's going to give us an error because we're borrowing it, but inc is already using it. Okay. So now that's interesting Because what it means to me is that I can't, if ink is incrementing count, then I can't increment count elsewhere. Like it's reborrowing, like trying to copy it into another variable. But can I say count plus equals 1 outside of ink? All right, I don't know. All right, let me yeah, I'm curious about this. What about if I wrote, can I undo changes? Oh, all right, you know what? This is a little tiny thing, so I'm not going to do it. Let's do it here. Here, in between, count plus equals 1. And let's run this. Oh. Compiling playground, cannot use count because it is mutably borrowed. Borrow of count occurs here. Use of borrowed count. Borrow later, use here for more information. Okay, yeah. That's what that means. Is that I can't, if I'm going to use it here, if I'm going to do this here in this closure, then I can't do it here. It's going to give me an error if I try to do it elsewhere. Ooh, that's interesting. That's interesting. Because what that means is, yeah, that's kind of cool. It means that I can't, I'm forced to increment through this mechanism. Okay, so that means that nobody else can accidentally also mess around with it. It has to be through the mechanism that I approve from messing around with it. Okay, all right, I get that. But the funny thing is that once I stop using increment, after that, then I believe, right? So we can go, yeah, hey, but, whoops, cancel that. We don't need to save that there. Where'd it go? Oh, there it is. Run. Okay. Yeah. It's happy. Count 1, count 2, movable 3. Oh, movable 3. We don't print this again. But I guess I can add that here just to see it. All right, run that. Yeah, 1, 2, 3, movable. Okay, so as long as ink is still being used, then I can't do this. So I can't insert one of these in the middle, but I can, after it's done being borrowed, then it's a free-for-all. That's kind of interesting, because depending on the order I do things in, I might, yeah, that's weird. So this is okay, but if I do like an ink down here, then it's not okay anymore. Yeah, it's not okay anymore. Why? That's a little weird, honestly, because I can see myself getting into all sorts of trouble with code, because if I wrote this, then wrote this, and then went, oh man, I need it one more time down here, suddenly code that was working before is now breaking. Interesting. Okay. Well, what are you going to do? All right, now what's going on here with the non-copy type? Box new. Mem drop requires T, so this must take type value. A copy type would copy into the closure, leaving the original untouched. A non-copy must move, and so a movable immediately moves into the closure. I think I know what you're telling me. So mem drop. Where's mem drop? Oh, that's a thing. Mem drop. That's something that. Okay, that's from that library, and I assume there's like a free drop. So this is how you release memory. Consume consumes the variable, so this can only be used once. Consume. Oh, all right, consume. It drops it. So movable no longer works. Okay. Oh, this is going to be fun. This is going to be very interesting, writing this code. There's all sorts of rules here. All right, what's this? Using move before vertical pipes forces closure to take ownership of captured variables. Move, needle, haystack, contains needle. Contains 1, contains 4, ampersand 1, ampersand 4. Okay. True, false. So, contains 1, yes. Contains 4, no. Fair enough. Because the vector has a 1 in it, does not have a 4 in it. Okay. Uncommenting the line above will result in a compile time error because the borrow checker doesn't allow reusing a variable after it has been moved. There are haystack. So haystack has moved. Removing move from the closure signature will cause closure to borrow haystack immutably, hence haystack is still available and uncommenting the line above will not cause an error. Okay, so now if I try to run this, I'm going to get an error because, hey, move occurs because haystack has type vector, which does not implement copy, I believe is what it's going to say. Variable move due to the use of the closure, move. And then we can't look at the length of haystack anymore because it's been moved. All right. Now, if I remove move, then and run this again, true, false, there's 3 elements in vector. Okay. Right. There's still the original 3. So why would I do that? Why would I move it? I guess because I've consumed it and I don't want anybody else to mess with it anymore. I don't know. Interesting. Like, I'm trying to figure out what the advantage would be of moving the thing so that nobody else could use it ever again. I guess it's kind of like freeing it. So, okay. But contains was called twice, and which means, but the move that was attached to the contains didn't affect the second one. So, okay. Let me try this. What happens if I put the move here? Okay, and then I'll take this guy and I will put him here. Oh, but that's going to give me a compile error, right? Right, so I can't run that because it's going to say, hey, you've moved it. Doesn't matter how many of these. Yeah, and if I comment this out, it's no different than what I had before. So that really, I can't get this to do something useful. Huh. So it's not a runtime thing where we could see what the output of this, whether the output of this would still be okay or if it's not going to fail. But this is failing at compile time, and so we never get to run this line of code because this has already failed to compile. Oh well. All right. Let's move on. As input parameters. While Rust chooses how to capture variables on the fly, mostly without type annotation, this ambiguity is not allowed when writing functions. When taking a closure as an input parameter, the closure's complete type must be annotated using one of a few traits, and they're determined by what the closure does with the captured value. In order of decreasing restriction, they are function funmut, once. The closure uses the capture value by reference, mutable t. Okay. So previously, that capturing thing was figuring it out for us, and it sounds like we may have to do it ourselves on a variable by variable basis to compile or capture variables to be restricted way. For instance, consider the parameter annotated as once. This special, right, that the closure may capture by, but the compiler will ultimately choose. Oh my goodness. Okay. Hey, try swapping these and see what happens. Where, oh, there's fun once. Apply F, where F generic type parameter. Okay, and F is a function, and apply to 3 F, function which takes the closure returns on I32. And what's, so apply, where's apply in this mess? Apply diary. Okay. What's diary? Oh, let diary equals. Oh, okay. Right. So what's happening is we're passing a closure as a parameter to the apply function. So we can build up a set of closures and then decide which one we're going to use, presumably, and then pass the right one in. So that, and then this fun once is going to, what's fun once going to do? The closure uses the captured value by value. Okay. Why is it called once? This specifies the closure may capture by, but the compiler will ultimately choose based on how the capture variables are used in the closure. Oh, so fun once is the most flexible. If a move is possible, then any type of borrow should also be possible. Note that the reverse is not true. If a parameter is annotated as fun, then the captured variables are not allowed. Okay. So, okay. So these two are specifying how you can use them. This one says, hey, you figure it out, how to use them. Okay. But why once? Why once is the key word for that? Okay, and then this one, double satisfies applied to 3's trait bound, so let double, so we're passing in x and we're going to return 2 times x, and we're passing in apply to 3 double, and then apply to 3, we're passing the function, this one, 2 times x, into here, and then we're going to return, we're applying that function to 3. Okay. Alright, I guess. And then presumably that returns 6. Alright, and this one, apply. The function is, I said, greeting. Greeting is by reference, requires fun. Mutation forces farewell to be captured by mutable reference. Now requires fnmut. Farewell. Oh, up here, mutable. And then I scream farewell. You can now sleep. Manually calling drop forces farewell to be captured by value. Now requires fnonce. Okay, so that, because we dropped it. Okay. Right, so we need the most flexible if we're going to drop it. We need mutable if we're going to change it. And we can just use fun if we're just going to use it. And these are all variables that are inside greeting and farewell. And so this, even though apply is outside, there's a where. There's where. What the heck? Where? Sorry, I didn't even notice that. We have a new keyword. Where? Okay. Where? Huh. Where? Okay. Just thanks for introducing that. Okay. Yeah. All right. So, all right. It says, hey, let's try these things and see what happens. So let's run it the way it is with the most flexible. And let's have a look down here. I said hello. Then I scream goodbye. Now I can sleep. Then I screamed goodbye. I said hello. Then I screamed goodbye. Exclamation mark, exclamation mark, exclamation mark. And now I can sleep. Okay. And then 3 doubled is 6. Okay. Now, let's change this to what? Let's see what happens. Is it going to be a runtime error or is it a compiler? It's a compiler error. This closure implements fnonce, not fnmut. Closure is fnonce because it moves the variable farewell. The requirement to implement fnmut derives from here, required by a bound introduced by this call. Okay. And yeah, okay. And then if I say fn, then I get a different error. Not fun. This closure is fnonce because it moves the variable farewell. Oh, the mem drop. Oh, that's weird. Huh. Okay. So it'll tell you. And I suppose if you just do fnonce. Now, what happens if you used fnonce but didn't use something that required it? Oops, cancel that. Would it tell you that you didn't need to use fnonce? Nope. So over-specifying, not a problem. Under-specifying, problem. Right? Because this required the fnmut and this required the fun, but only this one required the fnonce. And we got rid of that one, but it still said everything was cool. Okay, so over-specifying, not going to give us any warnings. Under-specifying will give you some compiler errors. Okay. All right. I think I have absorbed about as much, tried to absorb, about as much as I'm going to for today. So I think I'm going to call it here. And we'll look at the rest of this next time. All right. See you.